Okay, close your eyes for a second. Picture this. The most, I don't know, spectacular, violent thing the universe can do. The death of a star.
A supernova.
Right.
Yeah. An explosion so bright it can briefly outshine its entire galaxy.
Exactly. But they're not just fireworks, are they? These things, these supernovae, they're like the universe's factories.
Forging elements, yeah. The stuff that makes up, well, us. Planets. Everything.
The carbon, the iron, the silicon in
Yeah.
your phone. A lot of it started inside a massive star right before it blew up.
Cooked up in the core.
So today we're doing a deep dive into something pretty groundbreaking. A specific supernova, SN 2021 HEV.
Ah, yes. 2021 HIV. That one's special.
Right, it's 2.2 billion light years away, but it's given astronomers this unprecedented look inside a dying star's core.
It really has. It's like peeling back layers we've only ever theorized about.
So our mission today is to unpack this, how this one observation, it kind of confirms long-held ideas about how stars are built.
The whole onion layer model.
Yeah, exactly. But then it also throws this huge curveball, challenging how much stuff a star can actually shed before it goes boom.
It really pushes the limits on mass loss, way beyond what we thought.
We're talking about seeing inside a star like never before and, what that actually means for the textbooks.
It's a big deal. It reshapes some things.
And this isn't just some abstract space thing, right? It connects back to the building blocks of the universe, elements here on Earth.
Absolutely. It shows how science progresses, how one observation can suddenly enrich our whole understanding or complicate it.
Huh. Yeah, or complicate it. It's a reminder the universe has plenty of surprises left.
Definitely. Okay, so let's get into this. That onion comparison for massive stars. It's been the standard model for, what, decades?
Right. The idea is they're built in these layers, these concentric shells.
Like an onion, yeah. Each layer made of different elements, getting heavier as you go deeper.
So you start with the light stuff on the outside, hydrogen, helium.
Primordial elements, leftovers from the Big Bang, essentially.
Then you go deeper, and the star's internal furnace, the fusion process, cooks them into heavier things.
Right, so below the hydrogen and helium, you expect carbon, oxygen.
Then deeper still, neon, magnesium.
Keep going. Silicon, sulfur, argon.
Until you hit the middle, the core, which is iron.
An inert iron core, yeah. Fusion stops there. That's the point of no return, really.
Okay, but here's the thing, right? This model, it makes sense. The physics works out, but actually seeing those deep layers.
Almost impossible, or it was almost impossible.
Yeah, because they're buried under all the outer stuff. It's like trying to see the very center of an actual onion without peeling it.
Exactly. The theory was solid, robust even. But getting that direct observational proof of the silicon, the sulfur, the argon layers, that was the holy grail, observationally speaking.
You can model it on a computer, but seeing it for real across billions of light years, that's something else entirely.
Precisely. The observational hurdles were huge. You needed the right event, the right timing, the right instruments. A lot had to line up, which makes SN 2021 off so remarkable.
Okay, so let's talk about 2021, Polef. How did we even spot this thing?
It started with the Zwicky Transient Facility, ZTF. It's a survey telescope. Scans the sky for things that change, things that flare up.
Like supernovae.
Exactly. ZTF caught it in 2021, right as it was starting to brighten. And then the timing was just incredibly lucky.
How so?
Well, astronomers at the Keck Observatory in Hawaii, they were basically ready to go. Alex Filipenko's team, they had time scheduled on the Keck Eye telescope literally the day after ZTF found it.
Wow. Talk about being in the right place at the right time.
Seriously. They were able to quickly point Keck Eye and use its LRIS instrument, that's the low-resolution imaging spectrometer.
Which acts like a prism, right? Splitting the light.
Yeah, it breaks the supernova's light down into its spectrum, its chemical fingerprint. Getting that spectrum so early, just one day after discovery, was absolutely crucial.
Before the explosion, smeared everything out too much?
Exactly. It captured the signature of the material close to the sphere, stuff ejected just before or during the initial blast.
Okay, and this is where it gets really wild. What did that spectrum actually show?
Instead of just the usual hydrogen or maybe helium you might see in some stripped supernova, they saw these distinct signals. Narrow emission lines from silicon, sulfur, and argon.
Whoa. The stuff from deep inside.
The deep stuff. And they were highly ionized, meaning atoms stripped of lots of electrons. That tells you it came from an incredibly hot, energetic place.
Like the star's inner layers.
Precisely. They also saw some carbon, magnesium, and helium, but the silicon, sulfur, and argon, that was the shocker.
Because those elements have just never been seen directly in a supernova spectrum before. They're usually hidden.
Never, always buried too deep.
Yeah.
This was like getting an X-ray view right into the star's core regions just as it exploded 2.2 billion light years away. It's, yeah, mind-blowing.
Okay, so this one observation does two massive things at once, right?
It really does. On one hand, finally seeing that silicon-sulfur-argon signature, it's this incredibly clear confirmation of the onion theory.
Like, yep, the models were right. Those layers are really there.
Exactly. It's probably the best direct evidence we've ever had supporting that fundamental structure of massive stars. A huge win for the theorists.
Well, there's always a but in science, isn't there?
Yeah, always. The other side of the coin is, well, how did we see those layers?
Right. If they're normally hidden, something must have removed all the outer layers before the explosion.
And not just the outermost hydrogen and helium. Based on seeing silicon and sulfur, it seems like this star lost. Well, almost everything else too. Way more material than we've ever seen a star shed before it goes supernova.
So it was stripped down.
Dramatically. The lead author, Steve Schultz, he described it as being essentially stripped to the bone.
Wow, stripped to the bone.
Yeah, and Schultz made this key point. It shows us how stars are structured and proves that stars can lose a lot of material before they explode. Not only can they lose their outermost layers, but they can be completely stripped all the way down to the core and still produce a brilliant explosion.
So it wasn't just a little bit of shedding, it was extreme, which raises a whole new set of questions.
Exactly. How does that even happen? Senior author Adam Miller said it perfectly. This event quite literally looks like nothing anyone has ever seen before. He argued it tells us our theories are too narrow.
Our textbooks aren't wrong, just
Incomplete.
incomplete, exactly. Nature has more ways for stars to die than we'd accounted for. There must be these more exotic pathways.
It's that amazing moment where what we know meets something totally unexpected and our whole picture expands.
That's the exciting part of discovery.
Okay, so let's connect this back. How does this change our view of how stars make elements?
Right, the whole stellar nucleosynthesis thing.
Massive stars spend their lives fusing lighter elements into heavier ones. Hydrogen to helium, helium to carbon and oxygen, and so on.
Building up those onion layers we talked about, creating all the heavier elements that didn't come from the Big Bang.
Correct. And that fusion process creates outward pressure fighting against gravity.
Until you get to iron in the core.
Yep. Iron fusion doesn't release energy, it consumes it. So the furnace goes out, outward pressure stops.
And gravity wins. The star collapses.
Incredibly fast. Then rebounds outwards in that massive supernova explosion, scattering all those elements it created out into space.
Okay, so usually if a star loses its hydrogen outer layer, we might see the helium or carbon-oxygen layers in the explosion.
Right, those are called stripped envelope supernovae. We see those.
But seeing silicon, sulfur, argon in 2021, BSEF means what?
It means so much more was stripped away beforehand. Not just hydrogen and helium, but the carbon, oxygen, neon, magnesium layers. Basically, almost everything down to those silicon, sulfur, argon layers near the core.
The star was peeled incredibly deep,
Yeah.
exposing its elemental heart.
It's a whole new level of stripping, which leads to the big question.
How does a star get stripped to the bone?
Well, the researchers think it probably wasn't one single event. More likely, multiple episodes of violent instability leading up to the final bang.
Like the star was having convulsions?
Sort of, yeah. Schultz described these intense instabilities near the end of a star's life. They can cause the star to contract suddenly, which then triggers a huge release of energy, blasting off the outermost layers. And he suggests this could happen multiple times.
So, repeated eruptions, each one stripping more material away.
That's one leading idea, like the star is tearing itself apart bit by bit before the final collapse.
Are there other ideas on the table?
Oh, yeah. The team is looking at a few possibilities. One is interaction with a companion star in a binary system.
Like a neighboring star pulling material off.
Exactly, gravitational stripping. There's also this interesting clue they detected neutral helium in the material around the supernova.
Okay, why is that significant?
It's a bit puzzling, but it might point to a binary companion that was itself a helium star, shedding its own material through strong winds. It adds complexity.
What else?
Maybe just incredibly powerful stellar winds, far stronger than usual models predict, or perhaps one single massive eruption right before the supernova.
Or that repeating instability idea.
That seems quite likely, where the core pressure reignites fusion bursts that blast off layers repeatedly. It's probably complex, maybe even a combination of factors.
It sounds like figuring out the exact how is the next big challenge.
Definitely. And this event is so unique, it's actually pushing astronomers to create a whole new category for supernovae.
A new classification. How do we normally classify them?
Mostly by their spectra. The big divide is type I, which show no hydrogen, and type II, which do. Then there are subtypes based on other elements like helium or silicon.
And those subtypes often tell you how much the star was stripped before exploding.
Generally, yes, but SN 2021-way, with its deep stripping and those specific silicon-sulfur lines, it just doesn't fit the existing boxes.
So what's the proposed new type?
They're calling it type ein, because there's no hydrogen. Key for exposed, signifying those deep exposed silicon-sulfur layers.
Ah, U for exposed. Makes sense. And the N?
And for the narrow emission lines they observed. That tells us something about the conditions of the gas emitting the light, maybe less turbulent, denser.
So, type ein. The first of its kind.
The very first example. Which is exciting, but also means, well, we only have one data point.
Right. We need to find more of these type I supernovae to really understand them.
Absolutely. Adam Miller he said while they have a theory for how this happened, he wouldn't bet his life on it yet because it's just one example.
Science needs more data, more observations.
Always. This star highlights the need to find more of these rare events to build a proper understanding. We still don't fully get how nature made this one.
Okay, so let's wrap this deep dive up. SN 2021 GIF. An incredible look deep inside a dying star.
Saw those core elements, silicon, sulfur, argon, directly for the first time.
Which gave us powerful confirmation of that layered onion structure we've theorized about for ages.
Big check mark for the models.
But it also showed us a star stripped bare, losing far more material than we ever thought possible before exploding.
Challenging our ideas about stellar mass loss in a big way.
And maybe even giving us a whole new supernova classification, type ein.
A potential new branch on the family tree, yeah.
But the exact how did it get so stripped? That's still a puzzle.
A fascinating puzzle. Binary interaction, crazy winds, violent pre-supernova burps, or those repetitive instabilities. Lots to figure out.
And here's something to chew on. Think about this star shedding almost everything it made over its lifetime.
Yeah, discarding millions of years of nuclear fusion products.
Only to reveal elements made just months before the final blast. It makes you wonder, doesn't it?
What other extreme transformative processes are out there? Shaping stars, creating elements in ways we haven't even conceived of yet.
It just shows how much more there is to discover. The universe keeps surprising us.
That's the beauty of astronomy. Keep looking up.